Hi, my name is Gene Schrader, and this is a mini video course on floating point theory and practice on Cortex-M MCUs. And of course, this includes the STM32 MCUs. This mini course is just 2 videos, and the total runtime is a little under an hour. Now, I've done embedded development for many years and have not really used floating point very much. First of all, for some of the domains I worked in, like communications, there really wasn't a need for floating point. Also, floating point had a lot of overhead, especially years ago, and we used other techniques that I'll describe in this course. But these days, floating point units, or FPUs, that do floating point processing in hardware are becoming more common, even in inexpensive MCUs. So perhaps floating point would be used today more than it ever has before. Now, my motivation in this course came about because I'm also working on a video course on stepper motors and robotic kinematics. And I'm doing the kinematics in floating point. And I found that using floating point on like an STM32 MCU is a little more involved than I thought. There's more things you have to think about. And so I like to cover these kind of topics completely. And so I thought it would be best to have a course just on floating point. So this might not be the most exciting topic in embedded, but if you want to be a well-rounded embedded engineer, I think it's good to know a little bit about it.
So I'll go through the course objectives briefly. First, we'll learn about floating point in general, and this is more the theory part of the course. And we'll also see which Cortex-M MCUs support floating point units. Then we'll learn how to write C code that will use FPUs that only support single precision numbers, which are floats. This is the key to increasing your application speed. Then we'll see how the compiler generates code for floating point for the two cases of whether or not there is an FPU. This involves looking at assembly code, but this is straight line code and I keep it at a high level and it's not difficult at all. Finally, we use some benchmark software to see the floating point performance of different STM32s and the impact of using the FPU. So we compute a speedup factor for using the FPU. So this mini course is organized into 2 videos. The first video, the one where you're watching now, should give you all you need to know of how to write code that effectively uses an FPU on a Cortex-M MCU. So you could stop here, but of course I think you should continue on to the second video, and it covers objectives 3 and 4 above. It gives you the behind the scenes view of how floating point works in practice and how to verify your code is correctly using the FPU. I think the performance testing that is done is also quite useful to see. Just a few notes before I get started. This course is based on C, but it is simple C code, straight line code that's just doing floating point. I think you can be a complete beginner at C and understand it. The code is stored in this GitHub repo. This includes the performance benchmark code that we use in the second lesson. There really isn't that much code with this course. But that code is built on an infrastructure layer, and that infrastructure layer was developed in other YouTube courses I've done. So this repo contains the whole thing. Finally, feedback on the course is welcome and appreciated, particularly any things that you think were unclear or things maybe that I missed. So now I'd like to start with some background theory on floating point. Of course, floating point allows you to use numeric values like these listed here. I put some famous ones up here you might be able to identify. Importantly, they range from very large to very small values that you can't do with integers normally. Now, for many applications, or maybe most applications, floating point isn't needed at all. And at the beginning of the course I mentioned I have rarely used floating point in my career. One of the reasons is floating point is slow if you don't have hardware support for it. And another reason is there are alternatives to floating point based on integers. And one of the common techniques is to use scaled values with an assumed exponent. So for example, if you are working with temperature values, you store them as integers, but you store the temperature times 100. So there is an assumed exponent of 10 squared. Of course, you have to keep track of these assumed exponents when you're doing calculations. Another technique is the so-called Q notation. And it's similar, but what that does is takes an integer and defines a binary point within that integer. So for example, Q23.8 would typically be used with a 32-bit integer, and it would indicate that 23 bits are used for the units portion and of the value, and 8 bits are the fractional portion. And those don't add up to 32 bits because there's an assumed bit for as a sign bit. So there are then rules when you're working with these numbers of how addition, subtraction, multiplication, and so forth work, and in particular how the binary point is dealt with. And these rules are really a lot like when you do math, decimal math by hand on paper, and you have to keep track of the decimal point. So I worked on a system once, I think it was a software modem for wireless, and it used this Q notation. I don't think I wrote any code or very little code for it, but I did have to read the code from time to time just to understand what was going on with the math. So in this table we show the common types of floating point values. The rows are for the different precisions of the floating point types, and I'll go through them fairly quickly. The first one is single precision. It requires 32 bits or 4 bytes for storage. It has a little over 7 significant digits, and the exponent range is plus or minus 127, which is probably enough for a lot of applications. The next precision is double, and it's 64 bits per value or 8 bytes. It gives you close to 16 digits of significance and an even larger exponent range. And then finally we have quad, which takes 128 bits or 16 bytes per value, 34 significant digits, has a huge range of exponents. As you might guess, higher precision requires more memory and more processing power, or you might say that higher precision operations generally take longer. Now the IEEE produces, it's a technical society of electrical and electronic engineers, and they produce the most widely used standards for floating point numbers. And these standards include things like the bit layout and all the rules of floating point. It's actually quite complex when you get into the details. One of the important things that these standards define are a few special floating point values besides just normal floating point values. One is negative and positive infinity, which represents things like 1 divided by 0. There's another value called not a number, or NaN, to represent impossible values like the inverse sine of 1.1. There is no such outcome, or so no such value. So there are rules for how these special values work in calculations, and they try to behave in an expected way. So if you're doing some calculation and you get a result of infinity and you just use that result in further calculations, it will work. You'll get values back. If you take infinity and add any number to it, the answer is going to be infinity. However, if you have a number, say 10, and divide it by infinity, you're going to get 0, which is mathematically inconsistent. But if that's your application, you might want to know that there was an infinity floating around in there, because that's probably not, that might be worrisome. And with not a number, it's a little bit different. Once you get not a number, any computation that involves not a number is going to return not a number. You're just stuck with it. So now let's see how this relates to the C language. The C language has floating point types that map to the IEEE standards types that we just discussed, but the mapping depends on the compiler and the processor. So we're going to look at the GCC compiler, which we use for STM32, and it's used for many other processors. And we look at two processors in particular. The first one is the x86-64, which is used for many laptops and servers. And the other one is the Cortex-M, which of course we use for STM32. Starting with the C type of float, we see it maps to a single precision 32-bit value in both processors. And that should make sense. And a double maps to a double precision 64-bit value on both processors. And again, that seems to make sense. Then we get to the long double. And for an x86-64, it maps to quad, 128 bits. Seems to sort of make sense. But on a Cortex-M, it maps to a double, which is 64 bits. So on a Cortex-M, a double and a long double are actually the same thing. So why is this? I don't know for certain. Certainly it would be possible to do quad precision calculations on a Cortex-M in software, but perhaps it was felt this isn't a realistic scenario. They wanted to support, who's going to be doing quad precision math on an MCU. I don't know, but this is what we have. So we had these different floating point types in C. And so if you're designing an application that's going to use floating point, you need to choose a floating point type in your code. So there are various factors that could influence your decision, and I'll just go through them. One is the precision of the data you're working with. This is the natural thing to look at, such as the sensors. If you're working with fairly low precision things, a plain float is probably good enough. Another thing is real-time and memory constraints. As we know, more precision means more memory and more real-time. And it might be that you would sort of like to use doubles, but you just don't have the space or you don't have the real-time to do it. The final item here is a complex one, and that is numerical problems. And I'll first say there's a whole field of study in mathematics called numerical analysis that deals with this kind of issue. It's an important field of mathematics. So in this little diagram, I show inputs going into a box that is doing some floating point calculations, and then it generates outputs. Now the inputs maybe are sensor values that aren't terribly precise, don't require a lot of significant digits, and the outputs might be the same way. You don't really need a lot of significant digits, or you might. But the question is, what is going on inside the box? Now, with floating point, you can't represent values exactly. You have a limited number of bits. And so whenever you do calculations, you almost always have some amount of round-off error. With some algorithms, that round-off error is what they call magnified, or it accumulates. And what you get is, the effect is what's called numerical instability. That means that the outputs can have a high degree of error. You look at the equation, it looks fine, but in practice, your calculations have error in them. And the error might actually be erratic. In other words, normally the calculation is pretty close, but on occasion, based on the inputs, you get very high error. And that's why they call it instability. Now, if you're using lower precision variables, sort of by definition, you'll have greater round-off error. And with greater round-off error, there's a greater possibility of these numerical problems. Now, if your calculations are simple, you're doing some multiplies and divides, you probably don't have to worry about this. But if you're doing more sophisticated things, perhaps an iterative calculation, you could have issues. And this could be a factor that would force you to use higher precision floating types. So now we're moving from theory to practice. I'd like to start by talking about C language coding for floating point. The first thing I'll say is that the C language is somewhat biased towards double precision floating point numbers. So if you're trying to use single precision floats, you have to be careful. First of all, floating point constants such as 1.23 default to being a double. Now, if you want a single precision or float constant and not a double, you need to use the F suffix on those constants to tell the compiler it should be a float. And here's some examples on this listed here. There's also a suffix, by the way, for long doubles. Instead of F, it's an L. And you'll see in the next video lesson, it can be very important to make sure the constants are the correct type to get the most efficient code. The other thing is that common mathematical functions such as sine and log have double arguments and they return double values. However, there are equivalent functions with an f suffix such as sinf and logf that have float arguments and they return float values. And there are also functions for long double that use the L suffix. It's up to you to choose the correct function. Again, if you aren't careful with this, you might get code that is not as efficient as it could be. And finally, I'd like to say a few words about floating point exceptions. These are things like dividing by 0 or taking the square root of a negative number that don't have a standard answer. Now, the default behavior in C is that you will always get a floating point result, but it might be one of the special floating point values like infinity or not a number that we just talked about in the, previously. It's up to you to check for these values in your code if you need to, and often you need to. Now, the C language does have APIs functions that you can call that will tell you whether any floating point exception has occurred in the past. And you can also reset those flags. So maybe you do a bunch of calculations and at the end you can see if any exceptions occurred along the way. And there's also a way to have a trap or a hardware interrupt occur when a floating point exception happens. This is, for example, what happens when you do an integer divide by 0. However, from what I can tell, the GCC toolchain that's often used for ARM doesn't support either of these options. The only option is you check your results of floating point calculations to look for things like infinity and not a number. Now let's talk about floating point units, or FPUs. These are specialized hardware that quickly perform floating point operations like add, subtract, multiply, divide, and maybe some type conversions. A floating point unit contains its own set of general purpose registers, much like a CPU does, and you can quickly move data between the FPU's general purpose registers and the CPU's. And this happens a lot, we'll see that. A floating point unit is tightly coupled normally to the CPU, and that's, for example, how you can do these transfers of data back and forth so quickly. Floating point unit instructions are normally interleaved with standard CPU instructions. So as the CPU is executing the program, it will be doing some CPU instructions, and then it might hit a floating point instruction, and the floating point unit will handle that one. So the CPU and the FPU sort of go back and forth as needed to execute the program. In ARM terminology, a floating point unit is a type of coprocessor. And it's just good to know that terminology, and we'll see that in a little bit. Some Cortex-M MCUs have optional floating point units. And by optional, I mean when some company builds a part based on one of these MCUs, they may have the option of including an FPU in their part. So you can read this table. I only want to mention that all floating point units in these Cortex MCUs are single precision with the exception of the M7, which has the option of being either single precision or double precision. So for a particular part, like an STM32 part, you would just check the data sheet and it will tell you whether it supports an FPU. If it's an M7, it will tell you whether it's single precision or whether it also handles double precision. Now, you need to tell the compiler via option flags whether the MCU you are using has an FPU. This is so the compiler knows whether it should insert FPU instructions into the code or whether it should instead insert function calls to floating point library functions. Now, if there is an FPU, but it only supports single precision, then the compiler will treat single precision calculations differently from double precision calculations. And we'll see this again in the next video lesson. So with that background, I can now go through the details of what you need to do to make use of an FPU on a Cortex-M MCU. And we're assuming single precision FPUs only, which, as you saw, is the most common case. So first you need to ensure that the GCC compilation flags are correct. Now, if you're using an IDE, this might be handled for you, but it's a good thing to check. So you can read these two options. The first option is used when there is an FPU, and it's telling the compiler the specific model or type of FPU. And these names are sort of based on ARM information from ARM. The first tells you the floating point version number of the floating point hardware version number, and it's also telling you it's single point or single precision and that there are 16 registers in it. And if it's a Cortex M7, even if it's single precision, it will be floating point version 5. And the other option is telling the compiler that for floating point options to use the FPU hardware when possible. So the compiler will know in this case that double precision, it can't use the FPU. It's going to have to call floating point functions, but for single precision it can generate FPU instructions and do those in hardware. Then you have to assume or ensure that the floating point unit is initialized. Again, if you're using an IDE and it generates initialization code, this might be handled for you. Now all you have to do is set bits in a particular system register called CPACR. I think the CP stands for coprocessor. I'm not sure of the other letters. For reasons I don't understand, I haven't looked into it. The floating point unit is viewed as two coprocessors, coprocessor 10 and coprocessor 11, and you put ones in those bit fields. And this line of code here is based on the SEMSYS API, and it sets those bits. So it's really just one line of code you would want to do early in initialization. The next thing is you want to be certain you use the F suffix on floating point constants. So in other words, write 1.23F, not just 1.23. That's important because if you don't do that and you use these constants in calculations, the compiler is probably going to be generating code to convert everything to doubles in order to do the calculation, and you don't want that. And you won't be using the FPU. Another thing is to make sure you use the right mathematical functions. Make sure you use sinf, for example, and not sine. Again, if you use just sine, it's going to use software to do the floating point calculations, and it's going to be doing them in double, which you don't need. Finally, I just mentioned a couple compiler flags that might be handy. One of them, this first one, I'll let you read it, but what it's saying is telling the compiler if you do a conversion from float, or a promotion as they call it, from float to double, to provide a warning. Because if you think you're just using float, that shouldn't be happening, and you want to know if it does happen. I don't know all the scenarios where this works, but it can't hurt. The second option is telling the compiler to assume floating point constants are floats and not doubles. So, by default, they will default to double. Frankly, I don't really like this option. I think I would rather stay with the standard C language behavior and just be careful rather than use this option that changes the behavior of C. This option might be useful, I can understand, if you're converting a lot of existing code to use single precision floats. So I have a few more practical notes on using an FPU. So first, you might wonder about libraries, such as the math library, which is called libm. Is it going to use the FPU? And the issue here is that standard system libraries are normally pre-compiled, so you would think they are not affected by the compiler settings for your project. And that's true, but rest assured there is a solution, and that is that the GCC toolchain contains multiple pre-compiled versions of these libraries. In fact, it contains quite a few versions. And in particular, there are versions of these libraries that use the FPU versus don't use the FPU. So when you're building your project, the GCC compiler and linker uses your settings in order to choose the correct version of these libraries. I verified this for my project, which I built inside the STM32Cube IDE. However, this IDE is based on makefiles, so if you write your own makefiles, I expect this would work exactly the same. However, I didn't really look into the details of specifically how this works. Now, the thing is, for other libraries that you might get off the web or wherever, you need to look into FPU support, and maybe you build these libraries yourself, and then your settings would be used. It's just another thing to check. So finally, I think it's a good practice to ensure that you're using the FPU as expected. That's because it's not clear when you're running your code whether it's truly using the FPU in the way you think it is. And one way to do this is to look at the .list or the .map files that are generated or can be generated during a build. And I suggest you look at the list file. And what you will be doing is, one, looking for evidence of double precision calculations. If you don't think you're doing double precision and you see it happening there, you got to look into that. Another thing is to look for evidence of single precision calculations that are not using the FPU. That's definitely a problem that you need to fix. Now, it's not too difficult to do this, but rather than try to explain it here, I'll refer you to the second video where I go through a .list file. And there you'll see what it looks like when the FPU is being used versus when software functions are being used to do floating point. And you'll also see what it looks like when you're doing double precision, which will be software functions. Here are the prompts for this video lesson. I'm just going to show them briefly here, and then I'll go through each question one by one and give you my take on it. By the way, this last question, you probably don't have enough information to answer it. You might be able to figure it out. It is an interesting case. What are the values of x and y after this code runs? Well, the variable x will remain with its initial value. This is because a float only has 7.2 significant digits, but this value is using over 8 digits for units. So this value of 1 unit that we try to add to it has no significance, and it will have no effect. The variable y will become this value, just 1 added to it. This is because the original value is using slightly less than 7.2 significant digits for units. So when the 1.4 is added, there is space for the units part, and that gets added, but the fractional part would require more than 7.2 digits, so it's lost due to round-off error. What numerical stability problems might you have with this function? Well, when you're looking for stability issues, one of the problems can be subtractions. And so I look at this, these two values being subtracted, which are then a denominator of a division. The problem with subtractions is if these numbers are very close to each other, the round-off error that has come into play when calculating them might be greater than the true difference between these two variables. And in other words, the round-off error may be magnified. And in that case, the results could be erratic. So just to go a little bit further, in the field of numerical analysis, you would try to change how this calculation is done to avoid this kind of thing. And there are techniques of how you do that. What inefficiencies will occur in the following function? How would you improve it? Well, the problem is you have this function which takes a float as an input and returns a float. But you're using the sign function, which takes a double as an input and returns a double. So what's going to happen is the compiler, when it sees this sign, it'll say, oh, that takes a double. So the compiler will have to insert code to convert this float to a double. Then the compiler will call sign, which returns a double, and then the compiler will have to insert more code to convert that double result back to a float. Now to improve that, this function, it's simple. Just use sign f, and that takes a float as an input and returns a float. If x is a float, when is the expression x equals x not true? This is a tricky one. It looks like x equals x should always be true. How can this be? Well, the exception to the rule is if x has a value of nan, or not a number, then equality has no meaning. It's not a number. How can you do equality? And thus this statement will always be false. This is a good little trivia question you can ask your friends, and if you want to make it even more difficult, don't tell them that x is a float. Just say, when is this not true? And people will always think of all kinds of things with macros and whatever, but it's simple. As a contrast, a floating point value of infinity does have mathematical properties, including equality of sorts. You can ask a mathematician about this. It's probably not so simple. But anyhow, in C, two values of infinity are considered equal, and this would return true. So here I'd like to quickly summarize what we covered in this lesson. We found that floating point variables can represent a large range of values at the cost of more computing resources. There are floating point types of varying precision. Higher precision types require more computation and more memory. Choosing which floating point precision to use in an application depends on a number of factors, including how much resolution you need, what resources you have in terms of memory in real time, and taking into account possible numerical issues. The C language has floating point types that map to the standard floating point precisions, but that mapping depends on the compiler and the processor. Floating point units are hardware devices that perform floating point operations much faster than a general purpose CPU would do it in software. A number of the Cortex-M MCUs that are used for STM32 support FPUs, although most of them only support single precision. And then finally, to make use of a Cortex-M single precision FPU, certain initialization, compiler settings, and C coding practices are required. This is the end of the first video lesson in this course. There is one more lesson, and it goes behind the scenes of how the compiler handles floating point. It also includes some performance testing of floating point on STM32 MCUs, showing you the speed up of using the FPU. I think you'll find it interesting. And thanks for watching.